Quantum computers just beat classical ones exponentially and unconditionally. A research team has reached a major milestone in quantum computing, achieving an unconditional exponential speedup over classical computers. Using advanced error correction techniques and IBM's 127-qubit quantum processors, they tackled a variant of Simon's problem, proving quantum machines can now outperform classical systems in a way that's no longer theoretical. Quantum computers promise breakthroughs in fields like drug discovery, cryptography, and materials science, but that power has remained mostly theoretical due to one big challenge: noise. Errors that creep into quantum computations have long made these machines less reliable and often slower than classical computers. Until now, a team led by Daniel Lidar, Viterbi Professor of Engineering at USC, in collaboration with Johns Hopkins researchers, has demonstrated, for the first time, an unconditional exponential quantum speedup. Their work, powered by two of IBM's 127-qubit Eagle processors accessed via the cloud, has been published in Physical Review X under the title Demonstration of Algorithmic Quantum Speedup for an Abelian Hidden Subgroup Problem. There have previously been demonstrations of more modest polynomial speedups, says LiDAR. But exponential speedup is the gold standard. It's the strongest advantage we expect from quantum computers. Why this matters. The holy grail of quantum computing has always been to show that full quantum algorithms can outperform classical algorithms in scaling performance, not just by a fixed margin, but increasingly as problem sizes grow. An exponential speedup means that as the problem size increases, the quantum computer pulls ahead at a pace classical systems simply can't match, LiDAR explains. And most importantly, our speedup is unconditional. An unconditional speedup doesn't rely on any unproven assumptions about classical computing limits. Past demonstrations often hinged on the belief that no better classical algorithm existed. This one does not. It uses a known, hard problem, a variation of Simon's problem, to prove the point. The problem: Simon's game. Simon's problem is a foundational quantum computing challenge. It involves finding a hidden repeating pattern in a function, much like a high-tech guessing game. Players query a mathematical oracle, and once they find two inputs that yield the same output, they can deduce the secret value. Quantum algorithms can solve Simon's problem exponentially faster than any classical method. This problem laid the groundwork for Shor's algorithm, which threatens modern encryption. Solving even a variation of Simon's problem on real quantum hardware marks a historic leap. How they did it. Fatharapon Singh Kanipa, a USC doctoral researcher and first author, says the breakthrough came from squeezing every ounce of performance from current hardware. Here's how they made it work. 1. Input restriction. They reduced the number of secret numbers, or ones in binary, limiting complexity and minimizing quantum logic operations, thus reducing noise. 2. Transpilation optimization. They compress circuits to require fewer logic gates, making operations faster and more efficient. 3. Dynamical decoupling. The biggest game changer. This technique uses a carefully timed sequence of pulses to shield qubits from environmental noise, maintaining quantum coherence longer. 4. Measurement error mitigation. Finally, they corrected residual errors that still occurred during the readout phase of the algorithm. Together, these techniques allowed them to achieve the exponential advantage on real, imperfect quantum hardware. What this means for the future. We've now shown that quantum processors can outperform classical ones in specific scalable tasks, says Lidar, who also holds appointments in chemistry and physics at USC Dornsife. This performance gap is real and unconditional. It can't be explained away or reversed by classical algorithms. But he cautions against overhyping the result. This doesn't mean we've solved practical, real-world problems yet. Simon's problem is still theoretical, relying on an oracle that knows the solution in advance. Bridging from toy problems to practical applications like simulating molecules or cracking encryption will require even better error correction, larger quantum systems, and further noise reduction. Still, the research marks a turning point. What was once a hypothetical promise that quantum computers could one day deliver exponential gains has now been firmly demonstrated on real machines. In summary, quantum computers are no longer just theoretical tools. This breakthrough proves for the first time that quantum machines can outperform classical ones exponentially. The result is unconditional, free of assumptions. Real world quantum hardware can now execute full quantum algorithms with scaling advantages. It's a glimpse into the future where quant